Hello, welcome back. So in the last video, we spoke about recurrent neural networks for sequence modeling, wherein we took a problem statement of generating names. We solved it with a character level, developing a character level language model using a recurrent neural network. So um we defined it, described the equations, and then also went on to code from scratch, where we developed the data loaders, getting batch of datas, then writing model class, basically writing without class structure, where we wrote the weights and forward pass, backward pass, loss estimation, etc., and then also sampling from the trained model. So let's recap that quickly for a bit, for maybe next 5 minutes, and then we'll move on to LSTM, which is the main topic of this video. So we want to do the same things for LSTM but a bit faster, because we'll talk about what are the improvements of LSTMs over why LSTM was a better choice over the RNNs, and then we'll try to see how we can code it. So basically, in last video, we went through this notebook of you see, defining the um, batch of data. How do we get the batch of data? Then describing the embedding of the inputs, how the equations work out with linear combinations, and then applying 10H over those. So the inputs were transformed to hidden dimension projections with some projections of weight WXH. HT minus 1 was the hidden state of previous time step, uh, which was transformed to hidden state dimensions of for new time step calculation by WHH. Then once we have a hidden state for this current time step, we use it to get the um, predictions out of for that particular time step. So this is an optional quantity you can calculate out of the hidden state, but because we are predicting characters on the basis of the last character or last few characters depending upon the block size that we had defined. So let's say we had some batch size here. Okay, I think we'll look at it once we move on to our next stage, where we have ported this all of this code, initializing weights, setting grad requires grad true, then getting the batch of data, training the models for some number of iterations, etc. We have done all these things. Here is the generate as well. So I moved all this to uh, .python script, where we are reading the data, defining our vocabulary, mappings, vocab size, etc., splitting our data into train and test. We are defining a few hyperparameters. Okay, so I took a second there. So basically, I want to touch upon is that most of the notebook code that we developed in the last video has been ported to this Python script. All the hyperparameters function to get the batch of data, which with all the paddings. So right now we have all the data of names in all the in the new lines in a text file. So the names are of different lengths. Therefore, we have to work on some paddings. Then also we have defined this estimate loss function, which we are calling at certain intervals while our training is running in progress. So we call this, we get the losses for train and val set, and then we print those in some intervals. So here is the multi-layer RNN class that uh, is developed finally. Earlier it was a single layer RNN that we developed, but I have extended it to for multi-layer. So you see in our basic RNN weight initiation, it is just a single weight matrix of this dimensions, uh, which are doing batch processings, but because now we are stacking RNN layers on top of each other for multi-layer RNN, so we had to wrap them up in a list as per the n layers hyperparameter. So we get multiple layers parameters for each of those weights, biases, then for logits calculation, etc. So logits calculation has to be done only one from the topmost layer. The layers below that, whatever number of layers you have, you will just be getting the hidden layers from each of those RNN cell at every time step, and you will propagate them along at the or to the further next layer, next cell upwards. So that's why we don't have this defined as a list of multiple of stacked of this quantity. Then remaining things are same parameters. We are defining a set of parameters. Turning requires grad true. Defining call function, which would be a forward kind of function in PyTorch, basically an n dot module functionality. So we are unwrapping the shape of the batch and time from X from the inputs. We are initializing zeros as hidden states for each layer. So there are n layers, then embedding the inputs into tokens, then passing the input into the uh, forward pass. Basically for n layers we have to iterate, and for each layer based on the previous hidden input for that layer we have to pass it to get the new hidden state of that layer. So based on the hprev and the xt at the current time step, we keep on doing this. We update. So now for the next layer, the input becomes hidden state of the current layer. So that's what is being done in this iteration. And once for all these layers it's done, we can calculate yt, which is our logits basically, which would be on the basis of last hidden state of the last layer, topmost layer, multiplied with this weights and added with the bias, so linear transformation, and this would give us the logits. So this logits we'll use to get the loss, etc. In our training loop. You'll see. Uh, One more thing is, yeah. So in our this diagram here, I didn't mention that there was a tan h operation applied to this linear combination of x and t, xt and ht minus 1. There is a tan h operation applied, which we have done here in the forward pass, I believe. Yeah, so this is being done, but the figure doesn't contain it, so that was a mistake. But yeah, so the code is ported to this and it runs all fine. If you see multi-layer RNN, let's try to run this. Let me pull this down first. All right. Mm. So let's see if 62,000 parameters we are able to train this. So starting loss is 3.29, 3.29. All right, we are training it. So yeah, this system doesn't have GPU, so instead of waiting for this entire training to complete, we'll just move along. Uh, we'll come back to the simple LSTM class. I have written this. I'll walk you through this after we have covered LSTM theoretically. So model training code, forward pass, zeroing the gradients, forward pass, loss dot backward, then printing the loss at some certain intervals, at eval interval, then weight updates. I'm keeping the learning rate 0.1 and 0.01, which is not a very good learning rate, but given the simplicity of our problems, it shouldn't be a problem, and our network is also not very complex. Then after all this is done, model is trained, we are using this snippet of code to generate 5 samples, basically 5 names, initializing IDX with zeros, basically a 0 of 1 by 1 size, because our model needs tensor as input, b by t shape tensor as input. Hidden state also initialized at 0. Then we forward it to model, our input to the model to get a logits. Probability is calculated, then one sample out of that probabilities, concatenated with the IDA to our IDX tensor, and once we have generated 0 again, we print the name. So that's what we are doing. Let's see. So at after maybe 20,000 iterations, we were able to reach train loss 1.9, val loss 2.14, which is not bad. If you recall, in our neural network based language model, character level language modeling, we were able to reach 2.4 or something with the neural network of a certain context size or a block size. So this is also doing a decent job. I think this is taking quite a bit longer because due to multi-layer RNN, we have complexified the network, but given the problem statement of just predicting names of a few characters, let's say 5, 6 letters or around that ballpark, it might not be a very complex problem. But yeah, it's good to know that our model is training and it's working fine. The model that we wrote from scratch. So you see, it's quite doable to write a model, these kind of model from scratch, just using PyTorch tensors and some initialization methods, basically, and cross entropy kind of thing. So these things we have covered in previous videos, how we will do from scratch loss calculation using the negative log likelihood formulation. How do we manually work on the formula to calculate those? That's why we are now comfortable with using the functionality as is here, the PyTorch functionality. But yeah, so this is it. Now let's move on to LSTM, and then we can look at the code here for the LSTM basically. Okay, so before we move on to LSTM, we have to understand what are the problems, basic problems with RNNs. Main problem. So the main problem is the problem of long-term dependencies. So basically, this is a blog post from Chris Ola. This is a very popular blog post. Along with, there are two blog posts that I am going to refer for my video series on LSTMs. One is this blog post, Understanding LSTM Networks. It is quite old one, almost 10 years old now. Exactly 10 years old. Wow, what a coincidence. But yeah, and another is this Andre Karpathy's blog post, Unreasonable Effectiveness of Recurrent Neural Networks. This we'll do in the second part, but right now, to understand the basic concepts and theory before we move along to look at the code, let's look at this blog post. So recurrent neural networks is something like this that we discussed in the last video. Um the problems with it is, in case of problem statements where our context window is not as large, that let's say our problem statement of predicting names, generating names, was something very similar to this, wherein it was like, let's say for example, 6 or 7 characters name was a sample of data. Um, so that was one particular sample of data padded to a maximum length of that too was maximum of, let's say, 15 was the maximum length in our data. So that would be quite a short context length for this to handle, because the the characters down the line, towards the right of the name, towards the end of the name, would have fair decent understanding of what were the letters seen before, as in it isn't such a big context length that the letters coming at certain time step would have no idea what was the letters at the time step, let's say 20, 30, 40 time steps before that. So this is a quite fairly decent problem statement to solve, which should have been under control of RNNs. Therefore, we were able to do a decent job with RNN as well. But in problem statements where the context length gets very large, that let's say we are talking at this time step, the hidden state would have no clue of what has happened, what were the letters occur at this time step. If given this difference is very large between these two time steps, so if that gap increases, RNNs become tough to learn that connection between two distant time steps, because as the if you see if you look at the derivatives of this time step with respect to this time step in weights, it would be very minimal, because it's all the gradients are between range 0 and 1, and if you multiply a number between 0 and 1 multiple times, it gets to very small. So this would have very low impact in what is going on in here. Therefore, we needed a better way to do this, and LSTM network is one of those networks that try to solve that problem, and it did it very well. It was introduced by Schreiter and Schmid-Huber in 1997. So I don't know much history about this, but yeah. So this is how RNN cell would look like. You have hidden state coming in from previous time step. You have input coming in at current time step. We do a linear combination of both of these and then add them to go into a 10H activation. The output is basically simply a hidden state of the current time step, and it goes on to the as a one of the inputs to next time step as well. So this was a very simple operation going on, which was not ensuring that that information from distant time step in the past has been held properly or have some role at this current time step as well. So this is something that the LSTM networks introduces. Let me zoom in. So yeah, so basically, this complex operations, lot of simple operations, basically seeming to look complex going on at at any particular time step. So first, the top arrow that you see from left to right is something called cell state, which is kind of a conveyor belt that flows through entire time steps, which is not multiplied by any weights directly or any linear transformations, so that it has capability to propagate information from very old time steps to current time steps or also in future. But that information that it propagates throughout the context length of our inputs depends upon can has to be controlled with some regulations based on some operations of multiplying and addition happening at each time step. So what are these operations? Sorry, so this is called a cell state, and so this you can interpret as a long in the LSTM long short-term memory network, you can interpret this cell state as a long-term memory, which seldom gets which does get modified at every time step, but most more or less has information throughout. And this hidden state, which you see coming in the lower part of the time steps from previous time steps, is the short-term memory, which is also called hidden state or short-term, or the output of a cell, we can say, which is going in here as HT. So this is interacting with XT input at any time step to get all these operations done. So what the first operation that is done is called forget gate. This XT and HT minus 1, they are uh, linearly transformed to some hidden dimensionalities. They are then added together, passed through a sigmoid layer. Sigmoid layer is basically, it will squash all the inputs in a vector between 0 and 1. So this operation gives an impression of some vector that should decide um, how much of the values of this vector coming in are should be propagated forward. So this is also, these two vectors are of the same dimensionality, let's say n embed. So these two will get element wise multiplication, and this will decide, because it has values between 0 and 1, it will decide how much of each number in this vector gets propagated, how much percentage of each of this number gets propagated. Once we have this, so we need to update the cell state now as per the current, some information we need to add onto it based on the current inputs and hidden state now. So this again is done with these two operations, where sigma is something similar as to this, but these would have different weight matrices for transforming xt and ht minus 1, then sigmoid operation to get vectors between 0 and 1, a vector of the length n embed between all the values between 0 and 1. This would decide how much of the values from this gets propagated to add into cell state. So this is basically a tan h with the linear combination. We apply tan h activation. So a vector of the same length of values between -1 and 1 are given here. So these two are multiplied. This will decide how much percentage of values from this vector goes into it. So this is called an input gate, and this information is added to cell state, which forms the final cell state that goes into the next time step basically. Now once we have the final cell state from one time step, we have to use the cell state to form the um, to get the hidden state for this time step basically. So cell state is passed through tan h. It gets to scores between -1 and 1, and we get a gate vector for this. This is called, I think, there's no name to get this gate. Output gate. Sorry, yeah, output gate. So, or maybe let me use this picture. Yeah, so this was forget gate, this was input gate, this is output gate. So output gate vector will decide how much of the percentage of values from this 10H activation of cell state has to be propagated for hidden state. So we multiply this and this output gate values, vectors, element wise multiplication to get the hidden state. So this basically has really uh, good capabilities to solve the problem of long-term dependencies that was a big issue in recurrent neural networks. And we want to take it for a spin for different problem statements. But in this video right now, because let me switch my screen. Okay. So right now, I developed a simple LSTM class. So I'll walk you through this. This is being applied in this Python file on the same problem statement of predicting generating names, which is a character level language modeling. uh, Now here the context window is of the maximum length of the name that we had, which is 15, I think, uh, which is not a very complex problem to solve with LSTM, because if we want to really test the LSTM networks, their capabilities, we need to give longer sequences, try to generate longer sequences, etc. Then we'll be able to understand if there are some vanishing or exploding gradients happening or not, or we are able to capture the long-term dependencies. We'll come to it, but first let's look at the this basic simple class of LSTM model that we can define. So here the to initialize it, we'll need inputs as an embed, hidden dimension. An embed is basically the uh, uh, dimensionality of the embeddings for the inputs, for the input tokens. Hidden dimension is how long is the dimensionality where all of the hidden state cell states would be operating upon, and how many layers do you want of LSTM. So I am working on only one layer, but yeah. So I have not even implemented how this n layers would complexify the add one extra dimensionality to all these weights and then operations. I'm just keeping there at it there as placeholder. Right now, this is a single layer LSTM network. So there are multiple operations. We have initialized embedding layer, which takes in vocab size, lookup table of vocab size by n embed. So embedding all the tokens are encoded into an embed size dimensionality. Then main operation of the LSTMs are happening here. We have waits for forget gate, waits for input gate, cell candidate gate, output gate. So these four are the weights. Um, Let me do it this way. I'll keep it here, and also on the other side, let me keep this. All right. So first step is the forget gate. We are talking about this operation. So xt is multiplied with some weights and ht minus 1 is multiplied with some weights. So these are those weights. xf, x is transformed to f for forget gate input. H is transformed to f. These are x is going in as input. So n embed by hidden dimensionality, size weight matrix. This is hidden dim by hidden dim size weight matrix, because h is already of the same dimension. Bias we are initializing as 0. All these scalings are being done for keeping all the at initialization, keeping all the activations low, so that the 10H outputs are fairly saturated. They are in the active range. They are not saturated as in 1. They are most of them gets to 1 or minus 1. That's why I'm keeping the value of these weights pretty low. So this initialization method, like hyper initialization, we have discussed in the one of the neural network videos. By looking at the paper, that we have to divide this with some kind of square root of fan in, and then multiply with some gain. So instead of doing that exactly, we are just multiplying it with a small number to keep it small. So this set of parameters are to do this linear transformation and this linear transformation, adding with a bias with these three terms. Once it is done, we will apply a sigmoid to it. But similarly, we have weights for wxi, whi, which is transforming x and ht minus 1 to it gate, output of it gate, and this wxc, whg is something that would be used to get to the C bar T, which is a potential candidate that goes on to add some information to our cell state. So these weights would be used for that purpose. Now you see the dimension, the input and output dimensions for each of these weights are same, because in each of these gates and 10H activations, the input are same, xt and ht minus 1. Therefore, all the dimensionalities would look same. Then output gate, then output gate, we'll just do the same operations, WXO, WHO, which is transforming XT and HT minus 1 to output gate vectors. Apply the sigmoid functionality here. You'll get something that decides how much of the information from this 10H should be used. So that information basically would be coming from 10H of CT. So you see here, this 10H is directly applied over CT. That is what is being done. This is basically to get two logits from each of the hidden states at each state. So H transform to Y and Y. Now we wrap all these parameters together to make a self dot parameter. Requires grad2, grads true. Then what we do is, so we do almost similar things. We take in the t time step input tokens for entire batch, so it becomes b by n embed. We index into this t time step at for each time step in range of t, which is the maximum t basically, as per the given input. Okay, so initialization was also done for B and H, hidden state and cell state as zeros. So all this processing is done at the batch level, so you'll see an extra dimension of B everywhere. Then at each forward pass, we'll take the time step t, we'll calculate ft, which is forget vector that at the forget gate, IT vector at the input gate, OT vector at the output gate, and GT vector at the potential cell candidate that should be added to the cell state. So these four are calculated with the matrix multiplication, summation, and the applying of sigmoid on top of all those things. Each of them give vectors of shape B by H. And so therefore at each time step, cell state is updated with forget gate output multiplied with C, previous cell state, and then added to it is input gate multiplied with GT. So these two things, or rather, uh, so these two things multiplied and they are added to the this product. This is what this plus operation is being done here. Then to get the hidden state, we take tan h of C, the calculated C vector, and we multiply it with output vector that is computed here. So we get the current step hidden state. This hidden state is then used to create the YT, which is the logits at that particular time step. So we append it into the logits. And once we have logits for all of the time step in that particular X, we stack them all together along last dimension, so it becomes B by T by H. So for each example in B, for each time step, we have H dimensional vector, which is a logit, or rather I should say which is basically a mm, vocab size. Yeah. Yes. Okay. All right. So this is the simple LSTM network. We'll complexify this and apply it to different kind of data, textual data, maybe Shakespeare code, some poem generation, etc., etc. But for now, I think this should be decent enough to understand how a basic LSTM works. So let's take it for a spin. Simple LSTM. We are initializing simple LSTM with the default parameters n embed and hidden dimension, which is basically 64 dimensional embedding size for inputs and 128 dimensional vectors for each hidden and cell state. Batch size we are keeping at 64, and layers is not used in simple LSTM. So yeah, let's quickly run it now. So with the multi-layer RNN, we saw that this should be good time to compare as well. We saw that these were our outputs, loss, and the generations. So let's also see now what do we do with. So LSTMs, it gets to 10,000, 1,04,000 of parameters, whereas in multi-layer RNNs it was 62,000. So number of parameters with even a single layer of LSTM has drastically increased. Let's see what happens. So while this is running, let me let tell you guys about my plan. What I'm going to do next is, so this is a very long, lengthy, and detailed and nice blog post. I read it a couple of times, but not uh, thoroughly, because there are multiple. So initially, after once you get into the meat of the article, right, of this blog, what happens is this LSTM network has been applied to different kind of text data. So first is Paul Graham generator, then Shakespeare data, then there is Wikipedia data, then there is algebraic geometry LaTeX data. What else? Linux source code. Do we have anything else? Generating baby names, understanding what's okay. So the it has been applied to like 4 5 different kind of text data. So and this the code that's provided here is not in Python, is in Lua, which is quite old. I think it might not be used now. Lua language. At a time, Lua, Cafe Theano, these used to be, and Torch, they used to be in the languages that were used to develop deep learning models. But yeah, so this is what I want to reproduce using the multi-layer LSTM kind of networks that we have built from out of a simple LSTM layer. So we'll have to get into different data, and then pre-process them, get them ready, and then train the LSTM networks for those each of those data. So we'll have to do this, and we'll do it in next video possibly. But yeah, you see here, these are the models uh, um, in the .lua files. So basically what I want to do is I'll just take hyperparameters and what the model looks like, that idea from these codes. I'll try to understand those, and then re-implement or reproduce those things, similar things in Python, extend our current code base, and I'll try to also implement train models for each of these data basically. And I'll walk through what are the nitty-gritties involved in dealing with each of these different datas. Now one thing that makes it all of these is easier is all of these have been trained with a character level language modeling kind of problem statement. So that should not be a tough thing. At least the tokenization part and encoding part should be pretty easy. So I'll try to do that as soon as possible in next couple of days possibly, and then record a video about it. Let's take a look at the what happened to this. Cool. So now let's increase this. In our multi-layer RNN, we are able to reach well loss of 2.1. Here we are reaching well loss of 2.25 with same number of iterations. Here I'm printing gradient norms to see if the gradients are exploding or are not exploding or vanishing. So they are maintaining a decent range throughout the optimization process. You see this name generation: Alia, Ianis, Ertel, Way, Laydon. Ianis has been generated at both places, so there is some similarity. Adile, Adlines, Isa, Leon, Lena. So yeah, it's generating some decent words. Not sure if they are names. They must not be, because there's a lot of improvement that we could do depending upon based on our neural networks that we have trained with large context size, and in our previous videos we were able to reach to validation loss of 1.9 of that ballpark. But yeah, so it's good to see that we are able to build workable or functional networks from scratch, and they are training with loss going down, gradient norms not vanishing or exploding, etc. So I'll wrap up here and I'll come back with the code for multi-layer LSTMs, or we'll build it over the on the video, on live on the video, for all those different problem statements that I just referred to from this blog post of Andrika Pati. So I want to see if I'm able to reproduce all these to some degree or not. Okay, thank you.